Okay, now, we've learned how to do the Lewis dot structure, so we get an idea where the electrons are distributed. Now, what we are going to delve into is what the molecules kind of look like. When I say a kind of, we're going to be using a spatial relationship that's not actually there, meaning they're going to be, the atoms will be spaced apart. They're actually blobs overlapping in these particular angles and geometries that we're going to show you. With the process we're going to use is something called Vesper, VSEPR, which stands for valence shell. Now, valence shell is an old term used by chemists where every level that we have, every n value, 1, 2, 3, 4, 5, is a sphere with other things trapped inside of it, with the exception, of course, of the first level. And so scientists started calling those levels shells. So it's actually valence level, but it's named way back when shell was a thing. So valence shell, electron pair repulsion principle. This is the Vesper principle. Now, the electron pair repulsion simply means that pairs of electrons, when are in close proximity with other pairs of electrons, are going to repel because they're all negatively charged. And as a result, certain geometries and bond angles are created as a result. I'll get into what bond angle means in just a little bit. So I have here written on the board what I just talked about here. But the most important part of this is this little diagram right here. This is the Vesper chart. Now the Vesper chart has 4 columns. The first column is the number of sets of electrons, and I'm going to be doing another version of this on the board as well. But the number of sets of electrons, what I mean by sets of electrons is locations where electrons are found, and I will re-emphasize that in both of this. The resulting bond angles from the repelling sets of electrons. The number of bonds we have. Now, sets of electrons can be those unshared pairs of electrons that a lot of you forget to put over on your line structures. Those are considered sets of electrons. Any bond, a single bond is a set, a double bond is a set, and a triple bond is a set of electrons, because they're all located in the same area. And then the resulting geometry, what do we actually see? What geometric shape is created from what we have noticed? So this is something you're going to want to refer to, particularly to the next lesson when we get into more complex molecules. Okay, so let's, in order to get an understanding for this, let's make sure we understand the Lewis dot structures for this. So let me put another diagram right here so we can have here, we have sets of electrons. We have bond angle. I'm just going to bring in BA. It's written out in the chart. Then we're going to have number of bonds. And then we're going to have geometry. And we're just going to go right down the line with these, and we're going to see where all these things came from. Okay? So we'll start off first with carbon dioxide. Now, we've done the Lewis dot structure for this before, but just very quickly, let's do the circle and then the line. When the line is what we're going to use to determine the information that I want you to glean out of this. So the central atom is that carbon, because it's the first one mentioned. Remember, it's always the first atom unless that atom is hydrogen. And then carbon has 4 valence electrons. How do we know that? Because carbon is found in Roman numeral 4A. And the A columns is the number of valence electrons that we are using for those dot structure. We have 2 oxygens. Oxygen is found in column 6A, so it has 6 valence electrons. North, south, east, west, and out there, here, and here. That means these 2 signals are opposite each other. And then we'll north, south, east, west here as well. And since I've paired these two with that, I'm going to pair these two with that, so that means an unshared pair of electrons will be right there. Oxygen has 6 valence electrons, it's lacking 2 to be full. And remember, we take care of our outside electrons before we think about the inside electrons. So since it needs 2 electrons, we're going to show a double bond by using 2 circles around 2 pairs of electrons. Same thing over here, oxygen has 6 over here as well, lacking 2 electrons to be full. So I will show that. Now, that means then that the resulting line structure well, it's something like this. I moved the electrons around. I like symmetry. But here's the important thing. Our central atom is right here. I'm going to use an asterisk or a star to identify the central atom. You're going to be asked to do the same thing. You can use a star, or you can just write the word central atom under it. But now we're going to look at the locations or the sets of electrons around the central atom. Well, we have a double bond here, we have a double bond here. So that means that we have 2 sets of electrons around the central atom. Now, they're going to repel equally apart from each other, and they're going to go as far apart away from each other as they can. So it's going to create, if you imagine this as an angle where these are the endpoints of the angle and this is the vertex of the angle, that's going to be a straight line. So that measured angle is going to be 180 degrees. So the bond angle is 180 degrees. Okay? Now, the next part of that chart is the number of bonds. Well, even though this looks like it's 2 bonds, it's actually 1. That's why we call it a double bond. So we have a double bond here, a double bond here. We have 2 bonds. And that means then, and like I said, if you look at the structure the way it's designed right here, this is going to be a straight line. So we say that the geometry is linear. So we go to that chart, 2 sets of electrons, 180 degrees, 2 bonds, and the geometry is linear. Okay? Now, the next one that we're going to look at is sulfur trioxide. Sulfur trioxide is a pollutant. It's often the result of burning compounds that have sulfur, like coal. So there's a lot of this compound in industrial areas where coal is being burned. Now, the central atom then is the first one mentioned because it's not a hydrogen, so it's going to be S. I'm going to write that down there. You find S on the periodic chart, and you notice that it is like oxygen found in group 6A, so we have 6 valence electrons, north, south, east, west, pair. And then I'm going to have 3 oxygens going around it, all with 6 valence electrons, north, south, east, west. I'll have these 2 signals off to them, so that's going to go right there. And then I'm going to put 2 more oxygens. Now, here's the thing. If you remember from those special single bonds that we had, we only use them when we run out of spaces for single electrons to pair with each other. That's going to happen after this bond is created. So I'm going to put the other 2 oxygens next to these pairs of electrons. North, south, east, west, pair, north, south, south, north, east, west. And then let's pair this and pair this. So we know we're going to get 2 scenarios with those special secret bonds, but we're not going to do that until we lose all options of regular bonds. So since this oxygen has 6 and is lacking 2, it's going to take a double bond to pair them up like that. At this point, the sulfur has 2, 4, 6, 8 electrons. It does not want any more. So the special single bonds are going to be used here. Where this electron here is going to be moved, put it right there, and then you can have this single bond right here. That oxygen, this is going to be moved over here, and we're going to get a single bond right there. Now, even though this isn't the prettiest look, it look like a couple of ghosts running around there, but this is what happens. We get a special relationship in the lengths of bonds that we'll talk about much later on that shows that these are actually more space away from the sulfur than this is right here. But anyway, what we really get then is this double bond here, single bond here, and single bond here. And then we make sure everything is paired up with electrons that are not being bonded. So we got 2 pairs here, 3 pairs here, and 3 pairs here. So 2, 1, 2, 3, 1, 2, 3. And there's our Lewis dot structure for sulfur trioxide. Sulfur is the central atom, so I'm putting my asterisk right by that S. And if you take a look around the sulfur, I have 3 locations where electrons are found. This double bond, this single bond, this single bond are 3 different places we find electrons gathered together. So there's 3 sets of electrons. Now, that creates a situation where the electrons are going to space out as far apart as they can. This is not going to be very representative because this is 90 degrees, this is 90 degrees, and this is 180 degrees. What it's actually going to do then, I'm bring this up so you can see it better, it's going to look something like this. Now you can see that this is spread out. Now if you know your geometry, this is going to create a triangle, right? Well, the bond angle, if you put a point right smack in the center of an equilateral triangle, then the angle measure for this, while these are 60 degrees here, this angle degree right here is 120 degrees. So the bond angle equals 120 degrees. Okay? Now, stay focused on this structure right here. So we have 3 sets of electrons, which creates 120 degrees. Anytime you have 3 sets, you get 120 degrees. And then, the geometry, like I said, if you connect these points together, you get an equilateral triangle. Okay? But you have 3 bonds that is causing this to happen. Even though this is a double bond, that is considered 1 bond. So we have 3 bonds. And anytime you have 3 sets and 3 bonds, the geometry is triangular. And I've noticed a lot of textbooks from the college level are not even calling it triangular anymore. They're calling it trigonal-planar. Now, what does that mean? Well, trigonal, if you know gon, like polygon means side, tri means 3. It's a 3-sided plane or planar structure. Gee, what can we call that? Oh, I know, triangular. I don't know why they're doing it, but they are. So we go back to this chart. We have 3 sets of electrons, bond angle 120 degrees, because those are related to each other. We have 3 bonds here, and we said that is triangular. Or, we're going to open that up. Okay. Next.